हाँ जी. Good afternoon, students. Today, I am Guneet Kaur, Associate Professor in the Department of Electronics and Communication Engineering. And firstly, I will welcome to all of you in the 8th semester. Now it's your last semester, dear students. And I am teaching you the subject that is VLSI design. This subject is theoretical as well as practical. So there is a lab also. The subject code for this subject is ACEC 16702 and the subject code for laboratory or the practical is ACEC 16703. Okay, this is the subject that is VLSI design. VLSI, the full form for that is V for very, L for large, S for scale, I for integration. So it means very large scale integration. Actually, this subject is very important, and the base for this subject is digital electronics, which you have already did in the 3rd semester. In the 3rd semester, you read about combinational circuits, sequential circuits. In the combinationals like encoder, decoder, half adder, full adder, half subtractor, full subtractor. Now in this subject, the base is the DCLD, that is digital circuit and logic design or the digital electronics. And taking further that subject means taking further into to the DCLD concept, we will design the problems using this language. Actually, VLSI is a language. Programming part is also there. Now we will design our combinational or sequential circuits with the help of this language. This is actually a language. So before going into the detail of this subject, firstly, I want to discuss the program outcomes and course outcomes as well as the syllabi for this subject. In the next slide, I will discuss the program outcomes for this subject. Now going to the next slide, program outcomes. Program outcomes means after learning this subject, why this subject has been introduced. After learning this subject, the student will be able to apply so many program outcomes related to that. The first program outcome is apply the knowledge of mathematics, science, engineering fundamentals, and the engineering specialization to the solution of complex engineering problems. Now the second program outcome is identify. Actually, we have to identify formulation and then analyzing the complex engineering problems in the field of your stream, that is electronics and communication engineering. Now, the third program outcome, that is we have to design solutions for complex engineering problems and also the designing of the components which meets the specific needs in our cultural, societal, and environmental considerations. Next, program outcome 4. Use the research-based knowledge and research method, including the design of experiments, analysis, and interpretation of data, and synthesis of the information to provide the valid conclusions in the field of ECE, that is electronics and communication engineering. Next, further going to the PO5, create, select, and apply appropriate techniques, resources, as well as the modern engineering modeling for complex engineering activities in the field of communication networks. Next, apply reasoning by the contextual knowledge, assesses the societal, health, safety, legal and cultural issues, and the consequent responsibilities relevant to the professional engineering practice. The program outcome 7. Understand the impact of the professional engineering solutions in societal and environmental contexts and demonstrate the knowledge of and the need for the sustainable development. Next, the program outcome 8. Apply ethical principles and commit to the professional ethics and responsibilities and the norms of the engineering practice. Next, further going to the PO, that is program outcome 9. Ninth program outcome is function effectively as an individual or and as a member or and as a leader in the multidisciplinary settings. Next, the program outcome 10. Communicate effectively on complex engineering activities with the engineering community and with society at large, such as being able to comprehend and write effective reports and design documentation, make effective presentations, Next, program outcome 11. Demonstrate knowledge and understanding of the engineering and management principles and apply these to one's own work as a member or as a leader in a team to manage all the projects and in the multidisciplinary environments. Next, PO 12. Last PO program outcome 12 is recognize the need for and have the preparation and ability to engage in independent and lifelong learning in the broadest context of technological change. So, after learning this subject, you will get these program outcomes. Further, I will discuss with you the course outcomes, which means what type of technology, what type of concepts we will learn in this subject. Further, going to the course outcome, that is known as COs. There are 6 COs, course outcomes. CO stands for course outcome. And I will discuss it with you one by one. First is knowledge of the basics of hardware description languages. As VLSI is a hardware description language. What is the meaning of the word hardware description language? So actually VLSI is a language part. So we will make programs in this language. Hardware description language means hardware means we are using some physical device or the specification of physical devices like number of inputs, number of outputs. Then description means the language which is based upon the hardware knowledge of hardware of some system, that is hardware description language. In short form, it is known as HDL. H for hardware, D for description, L for language. In this, we will do the basics of that type of languages. Second is introduction to VHDL language. Okay. VLSI subject name is VLSI design. And under this, the language uses VHDL. VHDL. Where V stands for VHSIC. V stands for VHIC. VHIC full form is Very High Speed Integrated Circuit. And HDL stands for, already discussed with you. Sorry. HDL stands for Hardware Description Language. Means V, H for hardware, D for description, L for language, but V for VHSIC. And further VHSIC is known as very high, H for high, S for speed, I for integrated, and C for circuit. So, second course outcome is Introduction to VHDL language and its basics. Third course outcome is understanding the different types of structural models and statements used in VHDL. Okay, VHDL is a language, as I have already told you. So in any language, we have some statements, we have some models. So different types of models and the statements for using the programming, for doing the programming in VHDL will be discussed. Now the course outcome 4, that is designing of combinational and sequential circuits using VHDL. As I've already discussed with you, you have already learned about the combinational and sequential circuits in your DCLD, that is digital circuit and logic design. Combinational circuits are those circuits having no feedback. Sequential circuits are those having feedback. Example for the combinational is adder, half adder, full adder, half subtractor, full subtractor, multiplexer, demultiplexer, encoder, decoder, comparator. These all are combinational examples. Whereas in case of sequential circuits, we have flip-flops, registers, counters. We will do the designing in that using this language, VHDL. Now the course outcome number 5, that is knowledge of FSM. FSM stands for finite state machine. What does it mean? A machine which has finite number of states, that type of machine is known as finite state machine. And ASM charts. ASM charts algorithmic state machines, means which is based upon your algorithm, some sort of algorithm. So you will also learn this subject. Next is familiarization. Next is familiarization with different type of PLDs and their architectures. BLD stands for Programmable Logic Devices. Various type of programmable logic devices like FPGA, CPLD, PAL, PLA, these all will be covered in this and along with their architectures. So these are the 6 course outcomes for the subject VLSI design. In further slide, I will discuss with you the whole syllabus of your VLSI design subject. Your VLSI design subject is syllabus is divided into 4 parts. Part number 1, it includes actually 2 subparts. Firstly, introduction to this subject. Second is VHDL statements. In introduction part, we will cover the various CAD tools for digital systems. CAD stands for Computer Aided Design. Then, second topic is hardware description languages. Introduction to hardware description languages. In that particular, we will do the language VHDL. As you know, in any language, every language, in every language, there are data objects, data types, operators are different for different languages. So, next concept is to understand the various data objects, data types, and the operators used in this language. Then operator overloading concept. Next, entity and architecture declaration. The main programming part is to write the entity in this language VHDL. Entity and architecture is the part that is used in the programming. So, how to declare an entity, how to declare an architecture, this will be also learned. Next concept is introduction to behavior, data flow, and structure model. Actually, you can do the modeling, you can do the programming basically using the 3 models: data flow, structural, behavior. Along with, you can also have the mixed model. Mixed model, that is, you can apply 3 techniques in one system also. So, various type of modeling used in this subject will be learned. Next is VHDL statements. As you know that in any language, if we want to do the programming, then every language has its own statement part. There are so many types of statements used in any language. In this language, we are using the assignment statements, sequential statements, process statements, conditional statements, case statements, concept of array and loops, concurrent statements, then resolution function. So these all type of statements are helpful for doing the programming using the VHDL language. If we want to do the programming effectively, so we should have the knowledge. We should have the knowledge of all these statements, all these basic statements. Otherwise, we can't do the programming. So this is also the essential part in the syllabus. Next is, this was the part number 1. Now I will discuss the part number 2. So the part number 2, after learning the basic concepts, now we will apply these concepts to the designing part. As I have already told you, we will design the combinational circuit as well as the sequential circuit. In the combinational circuit, we will design multiplexers, encoders, decoders, code converters, comparators, and also implementation of Boolean functions using the VHDL language. So all these circuits will be designed using this VHDL language. Next, come on to the part number 3. In the part number 3, that is sequential circuit design and introduction to FSM. I've already discussed the full form, that is finite state machine, and algorithmic ASM, algorithmic state machine. In this part, we will review the flip-flops. Like you know that there are 4 types of flip-flops used. One is SR, second is D, third is T flip-flop, and fourth one is JK flip-flop. So firstly, we will review them, and after reviewing that, we will do the programming or modeling using this language. Now, next concept is introduction to FSM, that is finite state machine. Its various memory elements, their excitation functions, their capabilities, and The limitations of FSM. Memory elements included the D, T, JK, SR. Then their excitation table. After this, the concept is ASM chart, its components and its salient features. ASM stands for algorithmic state machines, means the machine's operations depends on the algorithm. Now, the part number 4, last part, that is introduction to the PLDs. Okay, PLDs stands for programmable logic devices such as PAL, PLA, GAL, FPGA, and CPLD and CPLD. So these all are your types of PLDs, and we have to also learn about the architectures for them. So full form for PAL is programmable array logic. PLA is programmable logic array. Next, GAL. GAL is generic array logic. Next is FPGA. That is field programmable gate array. Last is CPLD, complex programmable logic devices. So these all PLDs are covered in this chapter. So this was the introduction about the subject in the form of program outcomes, course outcomes, and the syllabus discussed in this presentation. Further, I will discuss with you the VLSI introduction, brief introduction. Then we will go into detail in the coming lectures. Okay, students, I'm going to start with the very first chapter, that is introduction and VHDL statements. Okay, firstly, I will do the VLSI introduction concept discussed with you. Now going to the next slide, VLSI introduction. Okay, as you know that VLSI stands for very large scale integration. Actually, this is based upon the transistor. As you know that a transistor is a fundamental semiconductor component in all the electronic devices. And the invention of the transistor was done in the 20th century. Transistors are simple, but their development time actually required many years of painstaking research. As you know that before the transistors, Individual electronic components were made, transistors were made as individual electronic components and were connected to other electronic components such as resistors, capacitors, inductors, and diodes on board to make an electronic circuit. And in earlier times, the computer was relied on the vacuum tubes and mechanical switches. But due to the inventions of the transistors, it is possible to reduce this size because transistors are much smaller than vacuum tubes and it consumes the less power. And the electronic circuits could be made actually more complex if with more transistors. And the switching speed for the transistors are much better than the vacuum tubes. Firstly, integrated circuit was made in 1958 and engineers put two transistors on a silicon crystal and creates the first IC, that is first integrated circuit. Then further onwards, scaling of transistors are done. That is, reduction in size becomes faster and faster due to the advancement in the technology. Now the transistor size has been reduced to 70 nanometer to 30 nanometer, 30, or 15 nanometers is also possible. In nano means 10 raised to power minus 9, means so much small size. Due to the small size, we are using the transistors in the VLSI. Sorry. As a result, today millions and billions of transistors can be placed on a chip. To make a good design, so lineage of VLSI technology actually began in 1833 when a researcher, that is Michael Faraday, that was the person which gives the measurement of electrical capacitance in the farad. First recorded the actually that person recorded the first semiconductor effect. Next, a remarkable achievement was made by Russell, Russell, inventor, in 1940. That person discovered the PN junction effects in the silicon. Sorry. So that person leads to the development of junction transistors. Sorry. Firstly, actually, semiconductor effect was invented. Second, junction transistors effective. In then after 1940, sorry, in 1947, the semiconductor technology entered a new phase when the researchers Johar Bardeen and Walter Brittain in the Bell Labs invented the semiconductor device known as point contact transistor. In 1958, Further inventions led to the first integrated chip. With further research on most transistors, after the invention of transistors, further invention was most transistors, that is metal oxide semiconductors. Then CMOS come, that is complementary metal oxide conductor, semiconductor. So, after inventing various types of transistors, it turned past to the logic families, which have you already done in your DCLD. And in 1960, TTL, transistor logic family, come into the picture and considered as revolutionary invention in the IC logic families. There are other logic families also like DTL, that is diode transistor logic, RTL, resistor transistor logic, ECL, emitter coupled. Then it is followed by the PMOS, NMOS, CMOS, P-type metal oxide semiconductor, N-type metal oxide semiconductor, CMOS complementary metal oxide semiconductor, then bi-CMOS logic families also come into the existence with the invention of various types of transistors. So these logic families were integrated on a chip with the SSI, MSI, LSI, VLSI, and ULSI chips. SSI, full form for that is small scale integration, and it includes the 100 electronic components per chip. Means one IC chip contains 100 electronic components. MSI, 100 to 3000 electronic components per chip. That is medium scale integration. Third is large scale integration. It includes number of electronic components from 3000 to 1 lakh. Then come into the next VLSI, very large scale integration, from 1 lakh to 10 lakh electronic components per chip. Next is ULSI, that is ultra large scale integration. It includes more than 1 million electronic components per chip. So we have seen that there is a continued improvement in the technology in the form of increasing the performance and productivity. So the development of integration techniques has followed the famous Moore's law. This law is given by the inventor Jordan Moore, co-founder of Intel in 1965. Gives the Moore law that the number of transistors per chip would grow exponentially, that is double in every 18 months. So as a result of this, there is a rapid development in the IC technology. More and more number of electronic components on a single chip, but it also continue to grow in complexity also. And design to these complex digital systems at gate and flip-flop levels also become very time consuming and tedious job. That's why the solution for this problem is we have a hardware description languages. So growing at such rapid pace in the digital design process. And hardware, that is HDL, hardware description language allows a digital system to be designed and debugged. Designed and debugging means debugging, that means removing the errors at the higher level before conversion to the gate and flip-flop level. So HDL is a computer-aided design tool for the modern design and synthesis of the digital system. There are two major hardware description languages. One is VHDL, second is Verilog, VERILOG, Verilog. In our syllabus, we have to concentrate only and only on the VHDL and go through the detail. So VHDL stands for VHIC. VHSIC, I've already discussed with you. V for VHSIC, that is very high speed integrated circuit, and HDL means hardware description language. It is actually versatile and powerful hardware description language. It can be used, this language can be used to describe the behavior structure and implementation of the electronic components. So we can say that VHDL is computer aided design tool. So this was the brief introduction to the VLSI or history of VLSI. In the next lecture, we will do the next concept, that is VLSI design flow. We will do this topic in the next. Now today I am finishing this lecture. Thank you.